Picture this. It's a Tuesday morning. You wake up, reach for your phone. Nothing. Dead. You figure it's the battery. You plug it in. Still nothing. You walk to the kitchen, flick on the coffee maker. Nothing. The microwave clock isn't blinking like it does after a power cut. It just isn't there. No light, no hum, no standby glow. You go to the window and look outside. Your neighbor is standing in the middle of the street, staring at his car. Not his phone. His car? The electric one. The one that hasn't moved. And then you notice the sky. Because even though it's morning, early morning, orange light just starting to bleed over the horizon, there's something wrong with the atmosphere above you. A shimmer, a faint curtain of color that has no business being visible in daylight. You've seen pictures of the aurora borealis. This looks like that, except it's not night, and you don't live anywhere near the Arctic Circle. You stand there on your front step in the early morning, silence, and you realize something that your brain is reluctant to accept. There are no sounds, no hum of traffic, no distant sirens, no aircraft overhead, not even the electrical background noise of a modern neighborhood, that subconscious, below-the-threshold hum that you don't notice until it's gone. Everything is quiet in the way that things only get quiet when they're broken. And then, slowly, it starts to dawn on you. It's not just your house. It's not just your block. It's not just your city. It's everywhere. Now I know what you're thinking. You're thinking, power cut, solar flare, something in the news cycle I probably half read last week. And you're not wrong to think that. But here's the part that nobody is really telling you clearly enough. And it's the reason we made this video. What's coming, what scientists are already watching in real time, isn't a regular solar flare. It isn't the kind of space weather event that takes down a satellite for a few hours and becomes a footnote in a science journal 3 months later. What we are potentially approaching is something that, the last time it happened, burned out telegraph machines across 2 continents, turned the night sky red as far south as Cuba, lit up the skies over Japan and Australia and the Rocky Mountains at midnight so brightly that people thought the sun had decided to rise 6 hours early, and shocked telegraph operators through wires that weren't even connected to a power source. Wires that had been fully disconnected, still sparking, still delivering current, because the energy coming from the sky was so intense it simply didn't need the batteries anymore. That event happened in 1859, and the sun is gearing up to do something very similar again. Now, before you click away thinking this is just another doomsday video, stay with me. Because this is not about fear. This is about something far more interesting than fear. This is about understanding what our star actually is, what it's truly capable of, why this particular moment in history is so scientifically significant, and what, if anything, can actually be done about it. We're going to go deep. We're going to get specific. We're going to look at real data, real science, and real consequences. And by the end of this video, you're going to look up at the sky a little differently than you did before. Let's start with 1859. Let's start with the last time it actually happened. Because if we don't understand what happened then, we can't possibly understand why what's happening right now on the surface of the sun should make every electrical engineer, every power grid operator, and every government infrastructure planner in the world lose a little bit of sleep. Chapter 1: The Last Time the Sun Let Loose. September 1st, 1859. Somewhere over the Atlantic. There's a man in England named Richard Carrington. He's 33 years old, independently wealthy, and extraordinarily passionate about astronomy. He's not a professional scientist in the institutional sense. He funds his own observatory, grinds his own lenses, keeps his own records. But he's meticulous in a way that most professional scientists of his era are not. Every clear morning, he does the same thing. He positions his telescope, projects an image of the sun onto a large sheet of white paper, and carefully sketches the sunspots he can see. He notes their positions. He notes their shapes. He notes whether they've changed since yesterday. Sunspots had been studied since Galileo's time, roughly 2.5 centuries earlier. But nobody had been watching them quite as systematically as Carrington. He'd been doing this for years, and he'd noticed something. The spots weren't random. They appeared in cycles. They drifted in latitude. They ebbed and flowed. He was building toward something important, and he knew it. But he wasn't ready for what he saw on the morning of September 1st. At 11:18 in the morning, as he was sketching a particularly large and complex group of sunspots, a cluster he'd been tracking for several days, 2 intensely brilliant white patches of light erupted from within the spot group. They were dazzlingly bright, brighter than the surrounding solar surface, which is itself blindingly luminous. The patches were roughly kidney-shaped, and they expanded rapidly. Carrington, understandably astonished, ran to find a witness. He needed someone else to see this. He needed confirmation. He ran, came back, and found that in the minute or two he'd been gone, the patches had already begun to fade. By 11:23 a.m., 5 minutes after they'd appeared, they were gone. He documented everything he could. He published his observations. Richard Hodgson, another British astronomer who had coincidentally been observing the sun independently that same morning from a different location, had seen the same event and published his own account. The two descriptions matched precisely. It was real. It was confirmed, and nobody, at the time, really understood what it meant. 17 hours later, the world understood. The impact. When the blast from the sun, a billion-ton cloud of magnetized plasma, a coronal mass ejection moving at several million kilometers per hour, slammed into Earth's magnetic field in the early morning hours of September 2nd, the results were immediate, global, and almost incomprehensible by the standards of the time. The auroras came first. The northern and southern lights, normally confined to polar latitudes, Scandinavia, Canada, Antarctica, exploded across the entire sky, not just at the poles, everywhere, in the Caribbean, in Central America, in the tropics, in Australia. Sailors in the South Atlantic reported being able to read by the light of the auroras at midnight. Gold miners in the Sierra Nevada mountains of California, men who worked brutal hours and slept like the dead, woke up believing it was dawn and started preparing for work. Well, 2 in the morning, the light was that bright. Red and green and violet curtains shimmered overhead. People prayed. People panicked. Some were certain the world was ending. The sky looked like it was on fire in every direction at once. In Rome, the Vatican Observatory recorded the aurora. In Japan, the phenomenon was documented by multiple observers. In Hawaii, in the Bahamas, in Queensland, Australia. The entire planet was lit up by the interaction between the incoming plasma and Earth's atmosphere. An atmospheric light show of a scale that no living human had ever seen. And while people were outside staring at the sky in bewilderment and terror, every telegraph office on Earth was descending into chaos. The global telegraph network of 1859 was the most technologically sophisticated infrastructure ever built by human civilization up to that point. Tens of thousands of miles of copper wire stretched across North America and Europe, under rivers, over mountains, through cities, and across farmland, connecting people in ways that had been unimaginable just a decade before. Before the telegraph, a message from New York to London took weeks by ship. With the telegraph, it took minutes. It was the internet. It was the smartphone. It was everything, all at once, and everyone who used it had come to depend on it. The Carrington Event destroyed it almost instantly. The geomagnetic storm induced enormous electrical currents directly into the telegraph lines. Currents that had nothing to do with the batteries installed at each station. The induced voltages overwhelmed the systems. Equipment sparked and burned. Fires broke out in telegraph offices in Boston, in Washington, in Paris, in London. The paper used to record incoming messages, fed through machines called paper tapers, caught fire from the arcing electricity in multiple locations. Operators received violent electrical shocks through their telegraph keys, the metal contacts they tapped to send messages. Some reports describe operators being knocked from their chairs. But here's the detail that really captures what was happening physically. At multiple telegraph stations across the United States and Europe, operators tried a desperate experiment. They disconnected their batteries entirely, completely removed the human-made power source from the circuit, to try to protect their equipment. And then they discovered something remarkable. The wires still worked. Induced currents from the geomagnetic storm were so powerful that they provided enough electricity to transmit telegraph messages without any battery at all. The sun was powering the world's communications network. And it was doing so at a level that was destroying everything it touched. In Boston, 2 telegraph operators, whose exchange was later published in the Boston Evening Traveler, communicated for several hours using nothing but the current induced by the aurora just to see if they could. "Please cut off your battery entirely from the line for 15 minutes, one sent to the other. The other complied, and the messages kept coming through, clear and legible, powered entirely by the magnetic storm overhead. It reads almost like science fiction. It wasn't. And yet, and this is the part that's easy to miss if you just skim the historical accounts, people survived. Society recovered. Within days, telegraph services were partially restored. Within weeks, most lines were back up. Within months, the world had largely moved on, catalogued the event as a remarkable curiosity, and returned to its business. Richard Carrington published his observations. Scientists argued about the connection between the white light flare and the subsequent storm. Life went on. That resilience is not a comfort, it's a warning. Because the reason 1859 was survivable is not that the event was small. It's that 1859 civilization was not yet dependent enough on electricity for the destruction of its electrical infrastructure to be catastrophic. In 1859, if the telegraph went down, you sent a letter. It took longer. That was the inconvenience. You didn't lose access to your bank account. You didn't lose your hospital's ability to keep patients alive. You didn't lose the pumps that push water through your city's pipes, or the systems that coordinate air traffic over the North Atlantic, or the satellites that tell cargo ships where they are in the middle of the Pacific Ocean. Every one of those systems, every single one, exists today. Every one of them is either directly dependent on electricity or dependent on systems that are dependent on electricity. And almost none of them were in any meaningful sense part of the world that the Carrington Event struck in 1859. That is the gap. That is the entire terrifying argument in a paragraph. The event hasn't gotten more dangerous. We have. The number that puts everything in context. Now, let me give you the number that frames the entire rest of this video. In 2013, researchers at Lloyd's of London, the 330-year-old insurance market that has spent centuries becoming very precise about calculating catastrophic risk, collaborated with atmospheric scientists at AER, Atmospheric and Environmental Research, to model what would happen if a Carrington-scale event hit Earth today. Their conclusions, published in a widely cited report titled Solar Storm Risk to the North American Electric Grid, were stark. A Carrington-equivalent storm could expose between 20 and 40 million Americans to power outages. Not a few days, not a week. The report estimated recovery times, the time needed to repair or replace damaged high-voltage transformers, restore grid functionality, and bring systems back online, at between 16 months and 2 years. High-voltage transformers, the massive steel and copper components that step electricity up and down between transmission lines and local distribution systems, are not off-the-shelf items. They weigh hundreds of tons. They are custom-built. Lead times for new ones under normal manufacturing conditions are 12 to 18 months. And a Carrington-class storm would damage or destroy hundreds of them simultaneously across a continent. The economic cost? Between $0.6 and $2.6 trillion per year. Of the outage? That's not the cost of the storm. That's the annual cost of the ongoing outage, while civilization tries to rebuild. And that's just the United States. That's one country. Europe, Japan, South Korea, Australia, India, every modern nation with a sophisticated electrical grid would be dealing with similar scenarios simultaneously. There would be no outside help coming, because everyone would be in the same situation at once. So the question isn't, could the sun do something like the Carrington Event again? It absolutely can, and has. The question, the one that's keeping space weather scientists genuinely anxious right now, is whether we are approaching another one. And the answer, based on what the sun is currently doing, is yes. Possibly. More likely now than it has been in over 20 years. Let's talk about why. But first, let me tell you about the time it almost happened again, relatively recently, and barely anyone noticed. The near miss that should have changed everything. July 23rd, 2012. A massive solar eruption occurs on the surface of the sun. 2 coronal mass ejections fire in rapid succession from the same active region, one behind the other. The second CME is moving so fast it catches up to the first and merges with it, forming a combined structure of extraordinary intensity. The merged cloud tears through the inner solar system at roughly 3 million kilometers per hour, among the fastest CME propagation speeds ever measured in the modern satellite era. It crosses the orbital path of Earth. Earth is not there. We had passed through that point in our orbit 9 days earlier. 9 days. In the context of Earth's year-long trip around the Sun, covering nearly 1 billion kilometers of orbital path, 9 days translates to roughly 22 million kilometers. That's the margin. That's the gap between the modern world as we know it and a scenario that planetary scientists, economists, and emergency management experts now refer to in policy documents as a low probability, high impact civilizational risk event. 22 million kilometers of empty space, and we're still here. The CME was later analyzed in exhaustive detail using data from the Stereo A spacecraft, which happened to be in the right position to observe the event directly. The results were alarming. The peak magnetic field strength of the cloud, as measured by Stereo A, was among the highest ever recorded for a CME in the modern era. Solar physicist Pete Riley of Predictive Science, Inc. published a paper in 2012 estimating the probability of a Carrington-class event occurring in any given decade at approximately 12%. His analysis of the 2012 CME suggested it was in magnetic intensity, comparable to or possibly exceeding the 1859 event, 12% per decade. Let that sit for a moment. That means in any given 10-year span, a single solar cycle, there is roughly a 1 in 8 chance that the Sun produces an event of Carrington magnitude. Some more recent analyses have placed the probability even higher, citing the frequency of near misses and large events in the observational record. A study published in the journal Space Weather in 2019 by researchers Ying Liu and colleagues estimated the occurrence rate of extreme events based on cosmogenic isotope records, traces left in ice cores and tree rings by cosmic rays, which are modulated by solar activity, and found that events of Carrington magnitude or greater may occur roughly once per century on average, with significant clustering around periods of high solar activity. Once per century. We're 165 years past the last one. The story of the 2012 CME made headlines. It got some science coverage. NASA put out a statement, and then it faded. Because nothing happened. Because we were lucky. Because the universe had positioned us just far enough out of the way, and we all went back to our phones and our streaming services and our algorithmically curated feeds. And the Sun went right on burning 93 million miles away, producing the energy that sustains all life on this planet, and also, occasionally, threatening to destroy the civilization that life has built. And now, right now, as you watch this, the Sun is ramping up again. Chapter 2, The Sun's Heartbeat, and Why Right Now Matters. Here's something most people don't know about the Sun. Something that isn't obvious from just looking at it. Which, to be fair, you shouldn't do directly. And something that took scientists decades to fully document. The Sun has a heartbeat. Not in the cardiac sense, obviously, but a rhythm. A roughly 11-year cycle of activity that has been observed, measured, debated, and refined since the 1800s. And this cycle, called the solar cycle, or sometimes the sunspot cycle, is the single most important piece of context for understanding why solar scientists are watching the Sun so carefully right now. Here's how it works, and why the mechanism behind it is so strange and so consequential. The sun is not a solid body. It is not a liquid in the conventional sense. It's a ball of plasma, ionized gas, electrically charged, moving, convecting, roiling, roughly 1.4 million kilometers in diameter. 1 million Earths could fit inside it. And unlike a solid object, different parts of the sun rotate at different speeds. The equatorial regions complete a full rotation in about 25 days. The polar regions take closer to 35 days. This phenomenon, called differential rotation, sounds like a minor technical detail. It is, in fact, the engine of the solar cycle. Because the sun's plasma is electrically charged, it carries magnetic field lines along with it as it moves. And when the equator is spinning faster than the poles, those magnetic field lines gradually get dragged, stretched, twisted, and wound tightly around the sun, like a rubber band being wound around a spool, tighter and tighter over time. After years of differential rotation, the magnetic field inside the sun becomes extraordinarily stressed, tangled, coiled to breaking point. Eventually, in regions where the magnetic pressure becomes intense enough, the field lines punch through the surface of the sun. These eruption points create areas where the local magnetic field suppresses the normal upward flow of heat from the solar interior, making those surface regions cooler than their surroundings. Cooler, in this context, means around 3,500 to 4,500 degrees Celsius, rather than the 5,500 degrees of the surrounding surface, which sounds hot because it is extraordinarily hot. But compared to the blazing surrounding photosphere, those cooler regions appear dark. We call them sunspots. At solar minimum, the quiet low point of the cycle, there are very few sunspots. The magnetic field has recently been reset, having flipped its polarity at the previous maximum, and the winding process is just beginning again. The sun looks relatively clean. Flares are infrequent. CMEs are smaller and rarer. Then, as the cycle progresses towards solar maximum, the magnetic winding intensifies. Sunspot numbers climb. Active regions form, areas of concentrated, complex, highly stressed magnetic field associated with large sunspot groups. And in these regions, the accumulated magnetic tension releases catastrophically and repeatedly. Snapping field lines reconnect in violent bursts, accelerating charged particles to near relativistic speeds and releasing the energy equivalent of billions of nuclear bombs in a matter of minutes. We observe these releases as solar flares, and in the most extreme cases, these reconnection events launch billions of tons of coronal plasma into space at millions of kilometers per hour. Coronal mass ejections. Solar maximum is where the danger concentrates. Every 11 years, the sun reaches this peak, sustains it for a year or two, and then gradually settles back toward the next minimum as the magnetic field finishes its flip and the winding process restarts. And we number these cycles sequentially, having started the count in 1755. We're currently in solar cycle 25. One more thing worth noting about this cycle length: the 11-year figure is an average, not a law. Actual cycles have ranged from as short as 9 years to as long as 14. The length and strength of each cycle are influenced by processes that solar scientists are still working to fully understand. Connections between the tachocline, a thin layer at the boundary between the sun's radiative and convective zones, the Hale cycle, a 22-year magnetic polarity cycle that underlies the 11-year sunspot cycle, and perhaps influences from planetary gravitational interactions that remain debated. We can predict cycle timing and approximate strength with some confidence, but with considerable uncertainty, as the spectacular failure of the Cycle 25 forecast demonstrated. And Solar Cycle 25 has a story that is genuinely extraordinary. The cycle that surprised everyone. When Solar Cycle 24 wound down around 2019, the scientific community's mood was cautious. Cycle 24 had been weak, one of the weakest solar cycles since detailed systematic records began in the mid-19th century. The peak monthly smoothed sunspot number had reached only about 116 compared to highs of 200 or more during the active cycles of the 1950s and the late 1980s. And a number of researchers, looking at long-term trends in solar activity, were beginning to suggest that the sun might be entering a prolonged period of quiescence, a grand solar minimum, similar to the Maunder minimum of the 17th century, when sunspots nearly vanished for roughly 70 years, and Europe experienced the coldest temperatures of the Little Ice Age. The NOAA Solar Cycle 25 prediction panel, convened in 2019 specifically to forecast the upcoming cycle, issued its official prediction: a peak smoothed sunspot number of approximately 115, with a maximum expected sometime between 2025 and 2026. A moderate cycle, unremarkable, roughly similar in strength to Cycle 24. The sun completely ignored this forecast. By early 2022, Cycle 25 was already tracking significantly ahead of the prediction panel's projections. By 2023, the monthly sunspot numbers were substantially exceeding the predicted peak, and the maximum wasn't even supposed to arrive for another 2 years. By late 2023 and into 2024, the numbers were extraordinary. Monthly average sunspot counts exceeded 150, 160, 170, levels not observed since the active cycles of the early 2000s. And the activity wasn't just more frequent, it was more intense. In February 2024, an active region designated AR3576 produced a series of powerful eruptions while positioned near the sun's central meridian, facing squarely at Earth. In May 2024, a cluster of active regions including OAR3664, one of the most magnetically complex regions observed in over 2 decades, fired off a series of X-class flares and associated CMEs over the course of approximately a week. Those CMEs arrived at Earth in succession, producing the most intense geomagnetic storm since the Halloween storms of 2003, a G5 event on NOAA's scale, the highest possible category, and the auroras came. They came in force. People in Florida saw them, people in Texas, people in Mexico, in northern India, in parts of Australia that almost never see auroras. Social media was flooded with photographs of green and red and purple curtains of light hanging over places that had no business seeing the aurora borealis. It was, by any measure, a spectacular and eerie reminder that the sun is not just a pleasant background detail of our existence. It is an active, dynamic, violent object, and we live in its direct line of fire. What most people didn't read beneath the aurora photographs The May 2024 storm temporarily disrupted high-frequency radio communications used by aircraft and emergency services. It degraded GPS accuracy to levels that pushed some precision agriculture systems, the kind that guide tractor implements to centimeter precision via satellite, into outright failure for portions of the storm. Some power grid operators in North America implemented temporary protective switching measures, deliberately isolating certain transmission segments to prevent induced current damage. Auroras are beautiful. The infrastructure effects they accompany are not. And Cycle 25 wasn't done. Through the second half of 2024 and into 2025, elevated activity continued. Additional X-class events occurred. Additional active regions of high complexity rotated across the solar disk. The sun maintained an intensity that solar physicists had not consistently observed since the years straddling the turn of the millennium. But here's the important thing about that May 2024 storm. The thing that the subsequent viral photo posts and excited news coverage somewhat obscured. That storm was not a Carrington event. It wasn't even close. The peak disturbance in Earth's magnetic field during the May 2024 storm, measured by the DST index, the standard scale used to quantify geomagnetic storm intensity, reached approximately minus 412 nanoteslas. The Carrington Event, reconstructed from historical magnetometer records at the Colaba Observatory in Bombay, one of the few instruments operating and calibrated well enough in 1859 to provide usable data, produced a DST excursion estimated at roughly minus 850 nanoteslas. Some analyses put it even lower. That means the Carrington Event was, at minimum, roughly twice as powerful in raw magnetic disturbance as the most intense storm of solar cycle 25 so far. And the Carrington Event itself may have been significantly more extreme than that minimum estimate suggests, since the Colaba data represents only a lower bound. In other words, May 2024 gave us a glimpse, a preview, a 50 to 60% strength rehearsal of something far worse that remains physically possible. And the cycle wasn't done. A tale of two cycles. To fully appreciate the significance of Cycle 25's performance, it helps to look backward. Solar Cycle 23, which ran from roughly 1996 to 2008, was moderately strong. It produced the Halloween storms of late October and early November 2003, a sequence of eruptions that included what was, at the time, the largest solar flare ever recorded by modern instruments. Designated X17 at first, then revised upward to X28, and in some subsequent analyses estimated at possibly X45, the November 4th, 2003 flare was so intense that it saturated the X-ray sensors on the GEOS spacecraft that were supposed to measure it. We couldn't even record its true strength. The instruments went off-scale. The associated geomagnetic storm knocked out power across parts of Sweden, permanently damaged or degraded dozens of satellites, disrupted aviation on transpolar routes, and forced the International Space Station crew to shelter in the Soyuz capsule to use it as a radiation shield. And this all happened during the declining phase of a moderate cycle. Solar Cycle 24, which followed, was significantly weaker. The Halloween-level storms did not recur. The cycle's maximum was underwhelming, and some part of the scientific and public consciousness perhaps absorbed a subtle false reassurance. Maybe the threat isn't so severe. Maybe the sun was calming down. Maybe we had time. Solar Cycle 25 has answered that complacency emphatically. It is stronger than Cycle 24 in essentially every quantitative metric. It has already exceeded the maximum that Cycle 24 managed to achieve at its own peak. And Cycle 25's peak is either currently occurring or still partially ahead of us, depending on which research group's analysis you consult. The smoothed sunspot number for Cycle 25 has already surpassed 150 in multiple monthly readings, a level Cycle 24 never approached. The sun woke up, and it woke up harder and faster than the people who study it for a living expected. Chapter 3: What scientists are seeing right now. And what it means? Let's get specific. One of the things that makes this topic difficult to communicate clearly is that it sits at a genuine crossroads of multiple scientific disciplines: solar physics, magnetohydrodynamics, space weather forecasting, geophysics, electrical engineering, and systems risk analysis. And each of those communities speaks in slightly different language about the same underlying phenomena. So let me try to translate as precisely as I can. Here is what solar scientists are currently observing, and here is what it actually means for the rest of us. Sunspot counts, the numbers that tell the story. The most basic, most accessible indicator of solar activity is the International Sunspot Number, a daily count of dark regions visible on the sun's surface, standardized through a global network of observatories coordinated by the Royal Observatory of Belgium. We've been tracking this number continuously since the mid-19th century, and with somewhat less systematic precision going back to the early 1600s. It's an imperfect proxy for solar danger. A single, large, magnetically complex active region can be orders of magnitude more dangerous than 50 small, simple, stable sunspot groups. But it gives us the clearest, longest historical baseline against which to compare current activity. In January 2024, the monthly average sunspot number exceeded 190, a level not seen since the early years of Solar Cycle 23, around the turn of the millennium. By some calculations, the smoothed sunspot number for Cycle 25 reached or exceeded 150 during its peak period, comfortably surpassing the maximum value achieved by Cycle 24. Multiple months in 2024 recorded raw sunspot numbers above 200, which means the sun's surface was, on those days, visibly peppered with dark magnetic features. What does this translate to in terms of physical danger? More active regions, more magnetically stressed, complex delta configuration sunspot groups, more opportunities for explosive reconnection events, more X-class flares, more CMEs launched into the inner solar system, more dice rolls. And the more dice rolls you run, the higher the probability that one of those rolls produces the specific unfortunate combination of factors: Earth-directed trajectory, extreme speed, southward magnetic field orientation, that leads to a catastrophic geomagnetic storm. The math is straightforward, even if the individual events are unpredictable. The X-flares, the sun's most violent language. Solar flares are classified on a Logarithmic scale, similar to the Richter scale for earthquakes. A C-class flare is 10 times more intense in X-ray output than a B-class flare. An M-class flare is 10 times stronger than a C-class. An X-class flare is 10 times stronger than M-class. Within each category, there's a numerical modifier: M1 through M9, X1 through X9. And for X-class, the scale technically has no upper ceiling. X10, X20, X28, X45 are all physically possible. The Carrington flare of 1859, reconstructed through historical records and comparison with more recent events, is estimated to have been somewhere in the X10 to X45 range, depending on the methodology used. During solar cycle 24, X-class flares were relatively rare. The sun produced perhaps 2 to 5 per year during its week maximum, none of them exceeding X6 or X7. During solar cycle 25, X-class flares have been significantly more frequent. The cycle has already produced multiple X5 to X9 events. An X9 flare in October 2024, one of the 4 strongest of the cycle at that point, produced significant shortwave radio blackouts across the sunlit face of Earth and demonstrated that the active regions responsible for Cycle 25's most energetic outbursts were among the most magnetically capable the Sun had shown in many years. None of those X-class flares has yet been followed by a Carrington scale CME aimed directly and squarely at Earth, but the potential is demonstrably there. The Sun has shown us repeatedly during Cycle 25 that it is capable of producing the kind of high-energy eruptions that, under the right geometric and magnetic conditions, could drive a catastrophic geomagnetic storm. We have seen the capability. We have not yet seen the worst-case alignment. The magnetosphere, our extraordinary shield, and its limits. Earth is protected from the continuous barrage of solar wind and radiation by its magnetic field, the magnetosphere, which extends tens of thousands of kilometers into space on the sunward side and stretches into a long tail on the night side that reaches hundreds of thousands of kilometers downwind. The magnetosphere is, in very real terms, the reason complex life exists on Earth. It has been deflecting the solar wind for billions of years. It redirects charged particles around the planet, funneling them toward the polar regions where they interact with the upper atmosphere to produce auroras, rather than allowing them to bombard the planetary surface directly. Without the magnetosphere, the solar wind would gradually erode Earth's atmosphere. We know this because we can observe it happening on Mars, which lost its global magnetic field billions of years ago when its core cooled and its dynamo shut down. Mars's atmosphere is now a thin whisper, less than 1% of Earth's atmospheric density, partly as a result of billions of years of unprotected solar wind erosion. Earth's magnetosphere is extraordinary, but it is not invincible. The key variable when a CME arrives is the orientation of the magnetic field embedded in the incoming plasma cloud. If the CME carries a magnetic field that points northward, parallel to Earth's own dipole field on the sunward side, the two fields repel each other. The magnetosphere resists compression. Reconnection is suppressed. The storm is relatively weak, even if the CME was very large and very fast. But if the CME carries a strong southward-pointing magnetic field, described technically as a large negative B-ZAL, the consequences are fundamentally different. The The southward CME field and Earth's northward sunward field are anti-parallel. They connect. They merge and reconnect at the leading edge of the magnetosphere in a process called magnetic reconnection. And when this happens, energy from the solar wind pours into the magnetosphere in quantities that can overwhelm the system. The magnetosphere gets compressed dramatically on the sunward side, sometimes to only a few Earth radii. The magnetotail on the night side becomes enormously elongated and then snaps and reconnects in violent substorm events, releasing stored energy explosively into the ionosphere. Enormous electrical currents flow through the upper atmosphere, what are called geomagnetically induced currents, or GICs, and these currents diffuse downward through the conductive ground, where they are picked up by any long electrical conductor, power transmission lines, natural gas pipelines, oil pipelines, submarine cables, railroad tracks. This is the mechanism by which a solar storm destroys things on the ground. It's not direct radiation. It's not charged particles hitting transformers. It's electromagnetic induction, the same fundamental physics that makes an electric generator work, operating at continental scale, producing slow, powerful, direct currents in systems designed to carry alternating current. High voltage transformers, which are the critical nodes of any modern electrical grid, are particularly vulnerable to these induced DC currents. A large enough GIC can overheat transformer cores, causing permanent damage that cannot be repaired in the field. And the brutally frustrating thing about the southward BZ, the one parameter that determines whether a given CME will cause a catastrophic storm or a moderate one, is that it cannot be reliably measured or predicted until the CME reaches the DSCO-VR spacecraft at the L1 Lagrange point, approximately 1.5 million kilometers from Earth. When a fast CME is traveling at 3 million kilometers per hour, the distance from DSCO-VR to Earth represents somewhere between 15 and 60 minutes of travel time. That's our warning window, not days, not hours, minutes. The warning infrastructure, what we have and what we're missing. SCO-VR, the Deep Space Climate Observatory, is the primary instrument standing between us and zero warning. Launched in 2015, it sits permanently at the L1 point, measuring solar wind parameters in real time and relaying them to NOAA's Space Weather Prediction Center in Boulder, Colorado, where forecasters monitor the data 24 hours a day, 7 days a week, 365 days a year. When a large CME arrives at L1, DSCO-VR measures the speed, density, temperature, and crucially, the magnetic field orientation of the incoming plasma. This data goes out immediately. Grid operators, satellite operators, aviation authorities, and emergency managers receive it. But DSCO-VR is old. It has exceeded its design lifespan. Its magnetometer, the specific instrument needed to measure the BZ, the critical southward versus northward field orientation, experienced instrument issues that temporarily compromised its reliability. NOAA has been working with aging data and backup systems for extended periods. The planned replacement, NOAA's Space Weather Follow-on L1 mission, SWFO-L1, was launched in 2024, but carries more limited instrumentation than a fully dedicated Space Weather Sentinel would require. There are proposals to station a next-generation space weather observatory at a gravitationally stable point ahead of Earth in its orbit. the L4 or L5 Lagrange points, from which it could observe CMEs much earlier in their journey from the Sun, providing hours rather than minutes of warning. The European Space Agency has been exploring the Vigil mission concept for L5 placement. NASA and international partners have discussed similar architectures. These missions remain in development. They are not flying yet. And while they are developed, debated, funded, and launched, a process that takes years to decades, DSCO-VR continues its aging vigil at L1. We are, in short, flying into a period of heightened solar danger with aging, partially degraded warning infrastructure, and a replacement that doesn't fully cover the gap. This is not classified information. Solar scientists and space weather forecasters will tell you this openly. The vulnerability is documented. The risk is known. The political and budgetary will to address it fully has been inconsistent. The active regions, reading the Sun's current face. The Sun doesn't distribute its danger evenly. The most threatening events come from specific active regions, areas of intense, complex, tangled magnetic field associated with large, irregular sunspot groups. Solar physicists classify these regions using multiple systems, but the key classification for our purposes is the one that identifies so-called delta sunspot groups, regions where sunspots of opposite magnetic polarity, north and south magnetic poles, are so closely intermingled that they share a common outer boundary, a penumbra, despite being of opposite polarity. Delta regions are, in essence, magnetic time bombs. The field between the oppositely polarized spots is under enormous stress. That stress releases as eruptions. Think of it this way. If you take two powerful bar magnets and force them together with their same poles facing each other, north to north or south to south, you can feel the repulsion. You have to work to hold them together, and if you let go, they snap apart violently. A delta sunspot region is doing something analogous but at planetary scale, across thousands of kilometers of magnetized plasma, with energy densities that dwarf anything humans have ever harnessed. And unlike bar magnets, the Sun doesn't just let go once and stop. It keeps building the stress back up. It can erupt from the same region multiple times over the course of days or weeks. The active region designated AR3664, which produced the major eruptions of May 2024, was a textbook delta region of exceptional scale, one of the largest and most complex observed in over 20 years. When it erupted repeatedly over the course of a week while positioned near the Sun's central meridian, facing approximately toward Earth, the resulting CMEs arrived in quick succession, stacking on top of each other and driving the geomagnetic storm that produced the global aurora display. After AR3664 rotated off the visible disk, scientists tracked what they could observe of it as it crossed the far side of the Sun, using helioseismic techniques and data from stereo spacecraft positioned at different orbital locations. And it eventually re-emerged on the opposite limb, somewhat diminished, but still active. It served as a dramatic illustration of a key point. The Sun doesn't just produce one dangerous region and stop. During solar maximum, it can maintain multiple active regions simultaneously, rotating new ones into Earth-facing positions on a roughly 2-week cycle. Here's a detail that's rarely discussed in popular science coverage of solar activity, but which professional space weather forecasters think about constantly. the concept of sympathetic eruptions. When one active region fires a major CME, the shock wave from that eruption, propagating outward through the corona, can destabilize neighboring active regions and trigger them to erupt as well. A single large eruption can set off a cascade, and in the historical record, the most damaging geomagnetic storms have often not been caused by a single CME, but by 2 or 3 CMEs arriving in close sequence, each one arriving while Earth's magnetic field is still compressed and disturbed from the previous impact. Under those conditions, Earth's magnetosphere is already partially open. Its defenses are partially down. The second or third CME hits a weakened shield, and the consequences are correspondingly worse. The Carrington Event itself may have been a compound event, 2 CMEs, one following closely behind the other, with the second one gaining speed by drafting through the cleared solar wind channel of the first. This cannibalization effect, as solar physicists call it, produces CMEs that arrive faster than their initial speed would suggest. Faster arrival means less warning time, and in a period of high solar activity, like the current peak of cycle 25, the probability of complex multi-CME events is substantially elevated compared to quieter periods. The prediction problem in this context is layered. We can identify dangerous active regions when they appear. We cannot precisely predict when they will erupt, at what intensity, in what direction, or with what magnetic field configuration. We can tell you that a Delta-class region near solar central meridian is a significant threat. We cannot tell you whether it will produce an X1 flare on Tuesday or an X10 on Friday, or nothing at all this rotation. The physics of the triggering mechanism, the precise moment when a field configuration becomes unstable enough to reconnect explosively, is not yet fully captured by our models. This is the fundamental limitation of space weather forecasting as it currently stands. And it means that the risk during solar maximum is not an event we can see coming clearly and prepare for specifically. It's a persistent, elevated background probability of catastrophe, one that demands systemic preparation rather than event-specific reaction. The question of what that preparation looks like, what we could actually do, what's already being done, and whether it's anywhere near sufficient, is what we'll turn to next. But before that, I want to do something that most coverage of this topic doesn't bother with. I want to walk you through what a Carrington-class event would actually look like hitting the modern world, not in abstract economic terms, not in policy document language. I want to reconstruct the hours and days of a genuine, direct impact, full-strength Carrington event in 2025. Because I think most people, when they imagine this scenario, imagine something cinematic and distant. The disaster movie version. The version that happens to someone else. I want to make it specific. I want to make it real. And I want you to understand, by the time we finish the next section, exactly what the stakes actually are. Chapter 4, the day it happens. Let me walk you through it, not in abstract terms, not in the language of risk assessments and policy documents. I want to reconstruct it the way it would actually unfold, hour by hour, decision by decision, failure by failure. So that when we talk about preparation in the next section, you understand exactly what we're preparing for and why the margin for error is so desperately thin. We're going to call this day Day 0. Hour -18. The sun fires. It's early morning somewhere in the Pacific. The sun's face is pointed at the night side of Earth. The Americas in darkness, Asia just waking up. On the solar disk, an active region that NOAA's Space Weather Prediction Center has been flagging in its daily forecasts for the past 10 days finally reaches critical magnetic stress. The field lines snap. A white light flare, the brightest kind, visible in optical wavelengths as well as X-rays, erupts from the region. Instruments aboard the GOES satellite immediately register an X-class event. The X-ray burst reaches Earth in 8 minutes, traveling at the speed of light. Radio communications on the sunlit side of Earth, which at this hour means Asia, Australia, and the Indian Ocean, experience sudden blackouts as the X-ray flux ionizes the upper atmosphere and disrupts high-frequency signals. Aircraft on Pacific routes lose radio contact for several minutes. Simultaneously, the eruption launches a coronal mass ejection. Billions of tons of magnetized plasma accelerated to somewhere between 2 and 4 million kilometers per hour, faster than most CMEs. The blast is powerful enough to cannibalize the remnants of a smaller CME that had been launched 3 days earlier, sweeping it up and merging with it, clearing the solar wind ahead. The NOAA forecasters see it immediately on the coronagraph imagery from SOHO, the Solar and Heliospheric Observatory. The CME's halo shape on the imagery tells them it's Earth-directed. They begin running propagation models, initial estimates, arrival in approximately 18 hours, with uncertainty of plus or minus 4 hours. They issue a G4 watch, a severe geomagnetic storm watch. They note that conditions are favorable for a potentially extreme event. They do not yet know the magnetic field orientation of the CME. They cannot. No instrument in space can measure that from this distance. They make a probability statement based on the CME's characteristics and the current state of the interplanetary magnetic field. There is an elevated chance of a strong southward BZ component upon arrival. Elevated chance. Not certainty, never certainty. 18 hours. Hour -15, the world is warned, sort of. The SWPC alert goes out. It reaches power grid operators in North America and Europe through NOAA's official channels. It reaches satellite operators, airlines, the Federal Emergency Management Agency, the Department of Homeland Security, the Department of Defense. In the United Kingdom, the Met Office's Space Weather Operations Center issues its own alert. The European Space Agency's Space Weather Service posts the forecast. Japan's National Institute of Information and Communications Technology sends warnings to their registered subscribers. And then the alerts hit a problem. The problem is not communication speed. The alerts move in seconds. The problem is the word elevated. The problem is the uncertainty band. The problem is that power grid operators have received similar warnings before, for events that arrived weaker than predicted, or arrived with northward BZ and caused only moderate disturbance, or arrived slightly off angle. The grid operators know that implementing emergency protective switching, the process of deliberately opening certain circuit breakers to isolate portions of the grid and prevent cascading induced current damage, is expensive. It causes planned blackouts. It affects hospitals, factories, data centers. It requires coordination between dozens of independent grid operators across multiple countries, each one making their own risk calculation. Some operators begin conservative protective actions. They put their highest voltage transformers on closer monitoring. They review their emergency protocols. They consult with each other. In some regions, pre-positioned protective relays are armed. But full emergency grid hardening, the kind that would actually protect against a Carrington scale event, is not implemented. Because the forecast still says elevated chance, not certain. Because nobody wants to be the operator who blacked out a city for nothing when the storm turned out to be moderate. Because the decision carries enormous consequences either way, and the information does not yet justify the most extreme response. 12 hours to go. The aurora oval expands. People at high latitudes begin seeing auroras earlier than usual. Amateur astronomers post photographs. Space weather enthusiasts on social media note that the incoming CME is looking significant. Hour -1. The truth arrives at L1. The CME reaches the DSCOVR spacecraft, 1 million miles from Earth. In this scenario, and this is the scenario that space weather scientists describe when they discuss worst-case events, the BC is strongly negative. Southward. Very southward. The magnetic field embedded in this plasma cloud is pointing hard in the direction that means maximum reconnection with Earth's magnetosphere. And the solar wind speed is reading above 2,500 kilometers per second. The density is high. The magnetic field strength is extreme. The SWPC computer systems update their models instantly. New estimates cascade out. This is not a G4 event. The models are now projecting a G5, maximum on the NOAA scale, and the DST index projections are going deeply negative. The numbers coming back from the models are numbers that the forecasters have seen before only in historical reconstruction papers about 1859. Emergency alerts go out immediately. The highest level notifications. Phones light up in grid control rooms across the continent. Hotlines between SWPC and major grid operators ring simultaneously. But here's the math. At 2,500 kilometers per second, the CME is roughly 1.6 million kilometers from Earth when it reaches DSCOVR. At that speed, it covers the remaining distance in approximately 640 seconds. 10 minutes and 40 seconds. In 10 minutes and 40 seconds, power grid operators must assess the incoming data, make individual and coordinated decisions about emergency switching, communicate those decisions to their control room teams, and execute the protective actions. In 10 minutes and 40 seconds, satellite operators must put their most vulnerable spacecraft into safe mode, rotating them to protect sensitive instruments. Aviation authorities must issue immediate emergency advisories to aircraft on polar routes. Military and government systems must activate their space weather emergency protocols. 10 minutes and 40 seconds. In a perfect world, with a well-practiced, pre-authorized emergency response framework, some of these things can happen. The grid operators who already armed their protective relays earlier in the day can execute switching orders in seconds. Satellites with automated safe mode systems can respond without human intervention. Some things can be saved. But in the real world, the world of jurisdictional complexity, of operators who have never actually experienced a real Carrington-scale event, of systems that have never been fully exercised under genuine emergency conditions, 10 minutes is not enough. Not for everything. Not for the grid. Hour 0. Impact the CME hits Earth's magnetosphere. If you could watch from space, you'd see the magnetosphere compress almost violently on the sunward side. The bow shock, the boundary where the solar wind is normally deflected, gets pushed in close, down toward the upper atmosphere on the sunlit side. The magnetotail on the night side balloons outward and then begins to whip violently as substorms cascade through it, dumping stored magnetic energy into the ionosphere in pulse after pulse after pulse. The aurora oval doesn't just expand, it explodes. Within minutes, auroras are visible at tropical latitudes. Red auroras, produced when high-altitude oxygen atoms are energized at 200 to 400 kilometers above the ground, wash the sky from horizon to horizon across large portions of North America, Europe, Asia, South America, and Australia. The sky turns the color of a coal fire. At midnight in Texas, you could read a newspaper, and in every long electrical conductor on the ground, every high-voltage transmission line, every continental pipeline, every stretch of railroad track, geomagnetically induced currents begin to flow. They don't flow dramatically. That's the thing. There's no sparking, no obvious visible failure. The currents are direct current, slow, steady, powerful. They push through transformers that are designed only for alternating current. They saturate the magnetic cores of transformers that were never built to carry DC load. And when a high-voltage transformer's core saturates, two things happen. It stops functioning efficiently as a transformer, which disrupts power flow, and it begins to overheat. Not fast. Gradually, over the course of minutes to hours, the heating is the killer. Because a high-voltage transformer's internal components, its copper windings, its insulating oil, its core laminations, are designed to operate within specific temperature ranges. When the core saturates under GIC load, temperatures climb. The insulating oil begins to break down. If the transformer stays online long enough under GIC conditions, the insulation fails. The transformer experiences an internal fault. It's gone. And a failed. High-voltage transformer in the modern grid is not a quick fix. These are not components that can be replaced from a warehouse. A single large EHV transformer, the kind that sits at a major substation and handles voltages of 345 kilovolts or higher, weighs between 100 and 400 tons. It is typically custom-built to the specifications of the substation it serves. It is manufactured by a small number of specialized facilities worldwide. Lead time under normal conditions, 12 to 24 months. Under emergency conditions, with multiple countries simultaneously competing for the same scarce manufacturing capacity, potentially longer. The United States has roughly 2,000 high-voltage transmission substations. A Carrington scale event, based on modeling studies, could potentially damage or destroy hundreds of the transformers within those substations. Not all of them. Not in every region equally. The damage would depend on the latitude. Higher latitudes experience stronger GICs. The local, ground conductivity, areas with resistive rock, like the northeastern United States, Canada, and Scandinavia, experience stronger surface GICs than areas over conductive sedimentary rock, and the specific design and protection status of individual transformers. But even if only 10% of critical transformers failed, Even if it were a relatively mild Carrington-class event, the implications are staggering. Hours 1 through 6, the cascade begins. Power failures propagate across the grid in the first hours following impact, but not uniformly and not all at once. Some regions, where protective switching was implemented in time, hold. Others begin to experience voltage fluctuations, frequency deviations, and automatic protective disconnections as the grid's own safety systems respond to abnormal conditions. The grid is designed to automatically disconnect parts of itself when it detects problems, to prevent cascading failures from spreading. But those automatic systems were designed for conventional faults, generator trips, line faults, short circuits. They were not optimized for geomagnetic disturbance, where the problem is pervasive and geographically distributed rather than localized. Large sections of the northeastern United States and Canada, high latitude, high-risk zones with resistive bedrock geology, begin going dark. The Northeast AC Interconnect, one of the 3 major interconnections of the North American grid, starts shedding load. Automatic protective relays operate. Transmission lines that carry power between regions are isolated. The grid fragments into islands of local generation and demand that must balance themselves independently. Some islands hold small regional grids with local generation, natural gas peakers, hydroelectric stations, manage to maintain frequency and supply power to their local areas. Others don't. The areas where transformers have failed have no local generation. They are simply dark. Cell towers, which typically have between 4 and 8 hours of battery backup, continue to operate initially. The Internet's backbone routers, housed in data centers with robust backup power, keep running. Emergency broadcasts go out. People are told, stay home, conserve phone battery, do not travel. But already, within the first 6 hours, the cascading problems are beginning. Water treatment plants run on electricity. The pumps that push water through city mains run on electricity. The pumps that run on electricity have backup generators, and the backup generators run on diesel, and the diesel tanks hold between 24 hours and 72 hours of fuel under normal operating conditions. Restocking diesel fuel requires fuel trucks, and fuel trucks require functioning roads and communication systems, and ultimately functioning refineries. Refineries run on electricity. Hospitals have backup generators. Most hospitals have 96 hours of fuel on site, sometimes more. They can operate, but they are already being inundated with patients. People on home medical equipment that has lost power, people injured in vehicle accidents in the dark, people with cardiac conditions exacerbated by stress and heat or cold. The emergency departments are full within hours. Financial systems begin experiencing problems. The stock exchanges, anticipating the storm, had proactively halted trading several hours before impact, a standard protective measure modeled on circuit breaker protocols for severe weather. But the payment processing networks, the ATM networks, the point of sale systems, these were not uniformly protected. In areas without power, they're simply offline. Cash is king, suddenly, in a society that has spent 30 years systematically eliminating the need for cash. GPS signals are disrupted, not eliminated entirely, but degraded. The ionospheric disturbance during the storm refracts and delays the GPS signals in unpredictable ways that make precision timing and positioning unreliable. For most consumer uses, this is an inconvenience. For the systems that depend on GPS timing for network synchronization, telecommunications networks, financial transaction systems, power grid frequency monitoring, the effects are more significant. Days 2 through 30, the long dark. This is where the scenarios diverge most dramatically, depending on two factors: the actual scale of transformer damage and the speed and coherence of the governmental response. In the best-case scenario, a Carrington scale event that somehow causes less transformer damage than Model's project, combined with a rapid, coordinated, militarized emergency response. Recovery might begin within weeks. Power might be restored to most affected areas within 3 to 6 months. The economic damage would be enormous but survivable. In the realistic scenarios that appear in risk assessments from organizations like FEMA, the Department of Homeland Security, and the Cambridge Center for Risk Studies, recovery takes much longer. The reason is the transformer bottleneck. You cannot restore grid power to an area whose main transformers have failed until replacement transformers are installed. And replacement transformers for extremely high voltage applications are not manufactured anywhere in sufficient stockpile to cover a continental scale failure. The United States has an emergency transformer program called REACE-X, the Recovery Transformer Program, which involves maintaining a small reserve of simplified, transportable transformers that can be moved to damaged substations and installed as temporary replacements more quickly than ordering custom units. REACE-X transformers are not equivalent to the permanently installed units they replace, but they can restore critical functionality while permanent repairs are made. The catch: the REACE-X stockpile is limited, designed for responding to isolated failures, not continent-wide damage. In a Carrington scenario, within 30 days, water distribution is severely compromised in regions without power. Sanitation is failing. Food supply chains have collapsed because refrigeration has failed, because fuel for transport has run out, because the distribution network has no electricity to operate. Communications are fragmenting as cell towers run out of fuel for their generators. Here's a detail that is almost never discussed in popular coverage, but which emergency planners consider one of the most acute secondary crises: fuel. Modern fuel distribution is a deeply electrically dependent system. The pumps at gas stations run on electricity. The pipeline pumping stations that move gasoline and diesel from refineries to storage depots run on electricity. The refineries themselves run on enormous quantities of electricity. In a widespread grid outage, the supply of liquid fuel to the general public begins to fail within 24 to 72 hours as local stocks are exhausted and the replenishment chain breaks down. Diesel for emergency generators, the fuel that hospitals, water treatment plants, and communication towers depend on, becomes the most critical and contested resource in the affected region almost immediately. Priority access to remaining fuel would almost certainly be commandeered by government authority. Military, emergency services, hospitals, and critical infrastructure would receive allocations. Everyone else waits. And in a multi-month outage scenario, the question of how to run the civilian economy without reliable fuel or power is one that no modern government has a comprehensive plan for, because the scenario falls outside the envelope of disruptions that modern society was designed to handle. The thing that policy analysts and emergency planners find most difficult to communicate to politicians and the public is not the immediate physical effects of the storm. It's the cascading logic of modern interdependence. Every major system in modern civilization was designed with the assumption that power would be available. Not unlimited power, not invulnerable power, but power that could be reasonably expected to return within hours or days after a disruption. Weeks of outage is the envelope of what most backup systems were designed to accommodate. Months of outage is simply not a scenario that the infrastructure was built to survive. The 2013 Lloyd's report estimated that between 20 and 40 million Americans could be without power for between 1 and 2 years. Let that number breathe for a moment. 1 to 2 years. Without refrigeration, without reliable water, without functioning hospitals beyond what generators can support, without the supply chains that bring food from farms to cities, without the communications infrastructure that allows commerce, governance, and emergency response to function. That is the scenario. That is what is physically possible, not inevitable, not certain, but possible. And it is possible in the next 18 months, based on what the sun is currently doing. Chapter 5. Can we prepare? What's actually being done? Here's the good news, and I mean that genuinely. This isn't the section where I grudgingly admit that someone somewhere is technically doing something. There is real, substantive work happening on this problem. There are engineers, scientists, policymakers, and military planners who understand the risk, take it seriously, and are working on it with real resources and genuine urgency. The question is whether what's being done is enough. And on that question, the honest answer is probably not yet, but the situation is improving faster than most people realize. Let's start at the top and work down. National and international policy slowly getting serious. In 2019, the United States government released a document called the National Space Weather Strategy and Action Plan. It was a revision and expansion of an earlier 2015 strategy, and it represented a significant step forward in treating space weather as a genuine national security and infrastructure threat rather than an academic curiosity. The plan laid out specific goals across multiple federal agencies: NOAA, NASA, FEMA, DHS, DoD, the FAA, and assigned concrete responsibilities for improving forecasting capability, developing emergency response protocols, and hardening critical infrastructure. In 2022, the UK government published its updated Space Weather Preparedness Strategy, which explicitly referenced the risk of a Carrington-class event and set out timelines for improving the resilience of critical national infrastructure, particularly the electricity grid. The European Union has been developing its own space weather frameworks, coordinated through the European Space Agency and the EU Agency for the Space Program. What's significant about these documents is not just that they exist, but what they commit to. They acknowledge, in official government language, that a severe space weather event is a credible, serious, near-term risk. They treat it not as a science fiction scenario, but as a natural hazard on the same planning level as major earthquakes, pandemics, or extreme weather events. And they mandate specific protective actions. The UK strategy, for example, includes a commitment to working with National Grid, ESO, the operator of the high voltage transmission network, to develop operational procedures for emergency protective switching that can be implemented quickly during a severe geomagnetic storm. It commits to maintaining stocks of critical spare parts, including some transformer spares. It commits to improving public communication about space weather risk. Are these commitments fully funded and fully implemented? Not entirely. Government strategy documents are aspirational as much as operational, but the direction of travel is real. Grid hardening, the technical challenge. At the engineering level, the problem of protecting power grids against geomagnetically induced currents is technically solvable. The question is cost, timeline, and political will to prioritize it. The most effective protection against GICs is a device called a neutral blocking device, or NBD. High voltage transformers connect to the electrical ground through a neutral point, and it's through this neutral connection that GIC typically enters the transformer. A neutral blocking device, essentially a large capacitor installed in the neutral circuit, blocks the DC component of GIC from flowing into the transformer while allowing the normal AC ground path to function. It's not a radical technology. The physics is well understood. The devices can be manufactured and installed. The barrier is scale and coordination. The North American grid has roughly 2,000 high-voltage substations. Installing NBDs at all of them, or even at the highest risk fraction of them, would cost somewhere in the range of $1 to several billion, depending on how broadly the hardening effort is applied and which substations are prioritized. That sounds like a lot. Compare it to the $0.6 to $2.6 trillion annual cost of an extended grid outage, and it's an extraordinarily cheap insurance policy. Compare it to the roughly $150 billion the United States spent on hurricane preparedness and response infrastructure between 2017 and 2022, and it becomes almost absurdly small. Yet, as of the time this script was written, the deployment of GIC protection devices across the North American grid remained patchy and inconsistent. Some utilities, particularly those in high-risk northern regions who had direct experience of GIC effects during past storms, had implemented protections. Many had not. The Federal Energy Regulatory Commission in the United States had issued reliability standards requiring utilities to perform GIC vulnerability assessments, but the standards stopped short of mandating specific hardware protections. The assessment requirement told utilities they needed to understand their risk. It didn't force them to fix it. In Europe, similar inconsistency exists. Scandinavian grid operators who experience GIC effects even during moderate storms, owing to their high latitude and the highly resistive geology of the Fennoscandian Shield, have generally been more proactive about hardening than their counterparts at lower latitudes. Countries like Finland, Sweden, and Norway have invested significantly in GIC monitoring and protection. The UK, whose geological characteristics also make it relatively GIC vulnerable, has been increasing its monitoring capabilities and exploring protective measures. The full hardware hardening across the transmission network remains a work in progress. The transformer stockpile. Question beyond real-time protection, the other critical resilience measure is pre-positioning spare transformers so that if some do fail during a severe storm, replacements can be installed more quickly than the normal 12 to 24-month manufacturing lead time would allow. The RECX program in the United States, as I mentioned earlier, maintains a small strategic reserve of specialized recovery transformers. The program has been expanded and improved since its inception, and the Department of Energy has been working with utilities to increase the stockpile size and improve the logistics of rapid deployment. A 2023 Department of Energy report on grid resilience included specific recommendations for further expanding the strategic transformer reserve as part of comprehensive space weather preparedness. Some larger utilities have begun maintaining their own strategic spares, keeping replacement units on site or in regional warehouses for their highest criticality substations. This is expensive because transformers are expensive, and because a transformer sitting in a warehouse represents capital invested in something that hopefully never gets used. But it's insurance. And the utilities that have done this risk calculation honestly have generally concluded that the insurance cost is worth it. There is a parallel worth drawing here with nuclear power plant preparedness. After the Fukushima disaster in 2011, nuclear regulators in the United States and internationally required utilities to pre-stage backup diesel generators, portable pumps, and emergency cooling equipment at or near nuclear plant sites. Equipment that could be quickly deployed in case of a beyond design basis emergency that disabled the plant's normal systems. The logic was straightforward. We cannot guarantee that catastrophic scenarios won't happen, so we can at least ensure that the tools needed to respond are physically present before the emergency rather than scrambled for in the chaos after it. The same logic applies to transformer stockpiling for space weather events. The tools exist. The strategy is conceptually simple. The barrier is the institutional will to treat the risk seriously enough to fund the preparation before the event, rather than regret the lack of preparation after it. The international dimension matters enormously here, because a Carrington-class event isn't going to selectively hit one country. It will hit the entire sunlit face of Earth simultaneously, and the night side hemisphere will experience the storm as it rotates into daylight over the following hours. The countries that experience the worst damage will be those at higher latitudes, but even lower latitude countries will be affected, and the global manufacturing capacity to produce replacement transformers is finite. In a world where Canada, the United States, the UK, Germany, Sweden, Finland, Japan, and South Korea all need replacement transformers simultaneously, the manufacturing queue is going to be very, very long. International cooperation on strategic stockpiling. Agreements between allied nations to maintain geographically distributed reserves that can be shared in an emergency is a relatively new but growing area of space weather policy. The G7 nations have discussed it. There are nascent frameworks for information sharing and mutual aid, but the kind of deep, binding, pre-positioned international cooperation that would genuinely accelerate post-storm recovery is not yet fully in place. Improving the warning system. Earlier, I described the DSCO VR spacecraft and the narrow warning window it provides. The scientific community has been working on multiple fronts to improve this situation, with mixed but genuinely encouraging progress. The first frontier is better CME modeling. Teams at NOAA, NASA, and international partner agencies have been steadily improving the physics-based models used to predict CME arrival time and, critically, the evolution of the magnetic field structure as the CME travels from the Sun to Earth. Models like ENLIL, a solar wind prediction model, and WSA-ENLIL, and newer approaches like EUHA-FORIA, European Heliospheric, forecasting information asset, are increasingly capable of providing probabilistic forecasts of CME arrival timing with smaller uncertainty windows. They cannot yet reliably predict BZ, the all-important southward magnetic field component, from a distance, but research is progressing. Machine learning approaches trained on decades of historical CME observation data are showing promise in identifying CME characteristics at the Sun that correlate with southward BZ at Earth. The second frontier is additional upstream observation. If we could observe the magnetic field structure of a CME significantly earlier than L1, say at a distance of 0.5 to 0.7 astronomical units from Earth, rather than the 0.01 astronomical units that L1 represents, we could potentially gain hours of additional warning time. The ESA Vigil mission, currently in development for an L5 vantage point, a location 60 degrees behind Earth in its orbit around the Sun, would provide a side-on view of Earth-directed CMEs as they propagate, giving scientists much better constraint on the CME's trajectory, speed, and potentially some information about its magnetic structure. Vigil is targeting a launch in the late 2020s. It cannot come soon enough. NASA's Parker Solar Probe, launched in 2018 and performing historic close passes of the Sun, is contributing enormously to fundamental understanding of how CMEs form and evolve in the inner heliosphere. It has made measurements from within the corona of the Sun itself, closer to the solar surface than any previous spacecraft. And the data it's returning is reshaping our models of coronal dynamics. The science it's generating will improve forecasting capabilities over the coming decade. Meanwhile, the ground-based monitoring network for GIC effects has been expanding. Magnetometer arrays across North America, Europe, and other regions measure geomagnetic disturbances in real time and feed data to both research databases and operational forecasting systems. These arrays give grid operators regionally specific information about the intensity and spatial structure of the GIC threat as it's happening, allowing more targeted protective actions than a global storm index alone can provide. What individuals can actually do? Here's the part of this conversation that most YouTube videos about solar storms skip entirely or handle so superficially that it's useless. What can individuals actually do? Not as preppers building a bunker, not as survivalists stockpiling for the apocalypse. Just as ordinary people who have internalized that this is a real, physics-based risk that exists on a timescale of years to decades, and who want to be reasonably prepared for the possibility that it happens during their lifetime. The honest answer is a moderate amount, and it matters. The most valuable thing an individual or household can do is precisely what emergency management agencies recommend for any multi-day to multi-week infrastructure failure, which is to say, for any severe natural disaster. That means maintaining at minimum a 2-week supply of water, roughly 1 gallon per person per day, either stored or accessible through a means that doesn't depend on electric pumping. It means maintaining a 2-week to 1-month supply of non-perishable food that doesn't require refrigeration or cooking on electric appliances. It means having a battery or hand crank radio capable of receiving emergency broadcast frequencies, because when cell networks go down, emergency radio broadcast becomes the primary public communication channel. It means having physical cash, because electronic payment systems are dependent on both power and internet connectivity. It means having basic medical supplies and sufficient quantities of any critical medications to survive an extended supply chain disruption. A particular concern for insulin-dependent diabetics, for whom refrigeration of insulin is a life-critical need. A few things that are less obvious but genuinely important. Printed maps. Not just the maps on your phone. Physical, paper maps of your local area and region. GPS, as I mentioned earlier, is degraded during major geomagnetic storms, and your phone's map application requires both an internet connection and a functional cell network to work reliably. A paper road atlas is not glamorous. It does not require a signal. In a communications blackout, knowing how to navigate to a hospital, a shelter, or a relative's home without GPS becomes unexpectedly critical. Similarly, a hand crank or solar-powered battery charger. Not for entertainment, though morale matters in an emergency more than people give it credit for, but for maintaining the ability to receive and transmit communications as long as any communications infrastructure is available. A partially functional cell network running on generator power might be intermittently accessible for days or weeks into an extended outage. Having the ability to charge a phone, even slowly, through a solar panel or hand crank means maintaining access to that intermittent communication window. None of this is exotic. None of it requires significant investment if phased in gradually over time. And essentially, all of it is useful not just for a solar storm, but for any of the other severe natural disasters: hurricanes, earthquakes, extreme winter storms, flooding, that are entirely plausible in most parts of the inhabited world. Beyond household preparation, the most impactful thing individuals can do is communicate pressure upward to local governments, to elected representatives, to utility companies. The grid-hardening investments that would genuinely reduce civilization's vulnerability to a Carrington event are not happening fast enough, largely because there is insufficient political will to prioritize them. That political will is shaped in a democracy by what citizens actually know about and demand. Most people don't know this risk exists. Most people, having never heard of GIC protection devices or strategic transformer reserves, have never thought to ask their utility company or their congressional representative whether these protections are in place. Political pressure from an informed citizenry has historically been the trigger for major infrastructure investment. The interstate highway system was built because Americans demanded connectivity. The rural electrification of the United States was driven partly by political organizing from communities who wanted power. The investments in levee systems, in seismic retrofitting of buildings, in hurricane-resistant building codes, all driven partly by citizen understanding of the risks and citizen demand for protection. Space weather preparedness is not yet a topic that generates that kind of organized citizen pressure. This video is, in a small way, an attempt to contribute to changing that. The scientific community. What researchers want you to know. I want to close this chapter with something that I think gets missed in most coverage of this topic. Solar scientists, space weather forecasters, and grid resilience engineers are not doomsday prophets. The ones who work on this professionally tend to be measured, technically precise, genuinely cautious about overstating both the certainty of catastrophe and the adequacy of current preparations. What they will tell you consistently is this: the risk is real, it is quantifiable, it is not negligible, and the cost of adequate preparation is far lower than the cost of the disaster. That's the message from every serious peer-reviewed risk assessment, from every major government strategy document, from every space weather conference proceeding I've read in researching this video. They will also note something that often gets lost in the public conversation. Progress is real. The scientific understanding of solar activity has advanced enormously in the past 2 decades. The forecasting models that NOAA runs today are significantly more capable than those available during the Halloween storms of 2003, the last time the world got a serious look at what extreme solar weather can do to modern infrastructure. The monitoring network is denser and more capable. The number of researchers working on this problem is larger. The international coordination between space weather agencies is better. The policy attention, particularly since 2015, has been more sustained and more substantive. None of that means the problem is solved, but it does mean that the trajectory is the right one. And it means that the resources and attention being invested now, during the peak of cycle 25, when the risk is at its highest and the evidence of what the sun can do is freshest, have the potential to meaningfully reduce our vulnerability before the next solar maximum arrives roughly 11 years hence. There is a concept in risk management called the preparation window, the period between when a risk is identified and characterized, and when the risk event actually occurs. In that window, meaningful risk reduction is possible. After the event, you're in response mode, and response is always more expensive, more chaotic, and less effective than preparation. We are currently in the preparation window for a potential Carrington-class event. The storm could come tomorrow, or in a year, or it could hold off until the next cycle entirely. But the window is open, and the investments being made in it, in monitoring, in grid hardening, in transformer stockpiling, in improved modeling, are investments that will pay dividends regardless of exactly when the next major event occurs. They will also tell you that the sun has been relatively cooperative, that the near misses of 2012 and other close call events happened to miss, that solar cycle 25 has been active enough to give the world some real, close-range experience with significant space weather, close enough to be instructive, not so close as to be catastrophic, and that the current period of high activity will eventually end, as it always does, and the sun will quiet back toward the next minimum. But they will also tell you that the next solar cycle will come, that the cycles do not stop, that 11 years from now, or 9 or 13, depending on the pace of the sun's own internal dynamics, another solar maximum will arrive. And if we haven't done the work between now and then, we will face it exactly as vulnerable as we are today. Possibly more so, as more of our infrastructure, our vehicles, our home heating systems, our medical devices, our food supply, migrates to electrical dependence. The window we're in right now, during the active peak of cycle 25, is itself a kind of warning system. It is the universe sending us the smoke alarm before the fire. The question is whether we're going to check the wiring or go back to sleep. Conclusion: what we owe the future. I want to end with 1859 again, but differently this time. Not with the terror of it, not with the sparking wires and the burning paper and the bewildered telegraph operators. With something else. With the person who noticed it first, who wrote it down carefully, and who tried to tell the world what it meant. Richard Carrington, after witnessing the white light flare on September 1st of that year, wrote a careful, measured account of what he had seen. He submitted it to the Royal Astronomical Society. He was, characteristically, precise about the limits of what he could claim. He described what he observed, he noted the subsequent geomagnetic storm, and he raised tentatively and with appropriate scientific humility the possibility that the two events might be connected, that what he had seen on the sun might have caused what had happened to the telegraph network 17 hours later. The scientific establishment was skeptical. The idea that events on the sun could physically affect events on the Earth was considered by many to be an extraordinary claim. The distance was too vast. The mechanism was unclear. Some prominent scientists of the era explicitly dismissed the proposed connection. They were wrong. Carrington was right. He didn't live to see his insight fully vindicated. The physical mechanism connecting solar activity to geomagnetic storms, the theory of magnetohydrodynamics, the understanding of the solar wind, the concept of the magnetosphere, wasn't fully developed until the 20th century, most of it after Carrington's death in 1875. But his observation was real. His connection was correct. And the careful, obsessive, every clear morning dedication to watching the sun and recording what he saw gave science a data point that has anchored our understanding of extreme solar events for over 160 years. I think about Carrington sometimes when I consider how we approach this risk today. We have tools he never could have imagined. We have spacecraft orbiting the sun at closer range than any earthbound telescope could observe it. We have magnetometers that can detect the faintest whisper of geomagnetic variation, and satellites that can photograph solar eruptions in multiple wavelengths simultaneously, and supercomputers that run global space weather models continuously, and a global network of scientists who share data in real time across every national boundary. We understand, in physical detail, that would have seemed like magic to Carrington, exactly what the sun does, how it does it, and why. What we haven't fully done is act on what we know. Not fully, not at the scale the risk deserves, not with the consistency and urgency that the science justifies. And I want to be careful here, because I don't think the right response to that observation is despair or panic. The right response is the same one that Carrington modeled in his own quiet way. Show up, pay attention, record what you see, tell people what it means, and keep pushing gently, persistently, with the confidence that understanding reality is always the first step toward changing it. There's a version of this story that ends with catastrophe. The CME fires during a period of peak cycle activity aimed precisely at Earth carrying a brutally southward magnetic field, moving fast enough to arrive with only minutes of warning. The grid fails across a continent. The recovery is agonizing, years long, defined by loss and difficulty, and the slow, humbling work of rebuilding something you'd always assumed was permanent. That version is physically possible. The science does not rule it out. But there's another version, and it's equally consistent with the science. The version where the investments being made right now, in forecasting, in grid hardening, in transformer stockpiles, in international coordination, accumulate quietly and effectively over the next decade. Where the next major active region on the Sun fires a Carrington-class CME, and the early warning systems detect it with enough lead time, and the grid operators who have pre-armed their protective relays execute their emergency switching in the critical window, and the most vulnerable transformers are protected, where the storm hits and the lights flicker and the auroras are extraordinary and the emergency response is intense, but the lights come back on within days or weeks rather than years. That version is also possible. It's possible if the preparation happens. It's possible if the political will catches up with the scientific understanding. It's possible if enough people understand the risk clearly enough to demand the investments that make resilience achievable. The sun is a star. It has been burning for 4.6 billion years. It will burn for approximately 5 billion more. It has no opinion about what we have built in its warmth. It has no knowledge of our electrical grid, our satellites, our financial networks, our hospital systems, our billions of lives organized around the assumption of consistent electricity. It simply does what stars do: burns, cycles, erupts. Occasionally, catastrophically, we are the ones with opinions. We are the ones who know what's coming and have the capability to prepare. We are the ones who understand the mechanism, not just in the vague sense of solar storms are dangerous, but in the specific, quantifiable sense of exactly which transformers are vulnerable, exactly which cities are at highest GIC risk, exactly which investments would most effectively reduce the damage, exactly how many months of warning we can generate with improved upstream observation. The knowledge is not the gap. The gap is between what we know and what we do about it. The last time the sun did something like this, the world's most sophisticated technological infrastructure was a network of copper wire and clicking machines, and the worst that happened was that people got shocked through their keyboards and some offices caught fire. The world absorbed it. The world moved on. If it happens in the next 2 years, the world's most sophisticated technological infrastructure is an interconnected, interdependent web of systems: electrical, digital, biological, logistical, that has never been designed to survive months of darkness. The world would absorb it too. Human beings are extraordinary survivors, but the cost in lives and years and suffering and the slow, difficult work of reconstruction would be unlike anything modern civilization has experienced. We have a window. We are in it right now. The sun is active, the risk is elevated, and the attention of the scientific and policy community is, slowly, imperfectly, but genuinely, turning toward this problem with more seriousness than it has managed in any previous solar cycle. The question is whether that window stays open long enough for the work to get done. And the only honest answer to that question is, we don't know. The sun doesn't negotiate. It doesn't wait for us to finish the transformer stockpile. or launch the L5 observatory, or complete the grid hardening assessment. It burns on its own schedule, on its own timeline, according to its own physics. All we can do, all we have ever been able to do, in every collision between human ambition and natural reality, is understand the risk as clearly as possible, prepare as thoroughly as resources and will allow, and keep watching the sky. Carrington would have understood that. Look up, once in a while, not with fear, with curiosity, and with the particular kind of respect that a thinking creature owes to a 1,300 trillion ton ball of nuclear fire that has been keeping this planet warm since before the first cell divided in the first ocean. The sun is doing something right now, something it hasn't fully done since 1859. Pay attention